Hey, it's time to talk about something new. So far we've really only had techniques that have worked with first order differential equations or very special second order, and this is one of those times too. But we're going to do a certain technique. So where we're getting in this class is we are going to start talking about some applications in a few more videos, and then past that we're going to talk about how we can how we can deal with higher order differential equations. So we're about to get there. We got videos before that, but right now it's kind of this thought like, are there techniques to deal with higher order differential equations? Yes, of course there are. And this is one of them. So how we can deal with some second order differential equations. Differential equations that have a second derivative of y with respect to x in them. Can we deal with them? And the answer is sometimes, a lot of times. If they're a certain form, definitely. This is one of those forms. So when we have something that we call a reducible second order differential equation, we need to know what that means, and then we need to know how to work with it. So what reducible means is that we can make a substitution, and in making this substitution, typically a variable that represents the first derivative. Okay, if the variable represents the first derivative, then the derivative of that variable would represent the second derivative. And then second derivative looks like a first derivative looks like a variable. Oh, okay, we reduced it one order into a first order differential equation that we can work with. But there's only a couple cases that actually work. So when's it work? This works if we have a second order differential equation where we are missing a variable completely, where we're missing y or where we're missing x. And there's two different cases, and we're going to talk about both of those cases. You might be wondering, well, what about the, it says two cases, there's a third one, and we'll talk about that in a minute. So when we have a second order differential equation that we are missing the y variable, I don't mean y to the first power, y to the second power, I mean just the function of y. Sorry, I said that wrong. Not the first derivative of y or second derivative of y. I mean just the function of y itself. We're missing the function of y, or when we're missing the function of x. I'm not talking about missing y, the derivative of y. I'm talking about y itself. We'll see that. We'll talk about it. But that's when we would call these a reducible first order differential equation. Sorry, reducible second order differential equation. When we can call the first derivative a variable, then the derivative of the first variable represents the second derivative of y, and we can replace both of them and reduce it by an order. That's the idea, and use one of the techniques we already know how to deal with. That's what we're looking to get out of it. So we're going to take a look at it, what to do, and then how to do it. So what to do, why this works, what's going to happen here. We're going to talk about just missing the y variable first in this video, and next video we'll talk about what happens when you're missing the x variable. So when we look at it, what if we were to call dy dx, so the first derivative of y with respect to x, just a variable? Well, then if p represents the first derivative of y with respect to x, then wouldn't the second derivative of y be represented as the derivative of p with respect to x? I mean, shoot, if p represents the first derivative, then the derivative of p would represent the second derivative, and that's exactly what we're going to do. And you go, well, wait a minute, it's that easy? Yep, that's it. If y is missing, it's that easy. What about all the other y's? I mean, don't you have to have a substitution for y? No, that's the whole point. Y gone. So if y is gone, we don't have to replace y with anything. That's why this technique works. So we say, okay, call the first derivative of p, then the second derivative is the derivative of p. That's it. If the first derivative is p itself, the derivative of p would represent the second derivative of y. That's the idea. Now, what about x gone? We're not dealing with it in this video, but the next one we will. Well, we do the same thing, and we go, okay, well, then y prime would equal dp dx, sure, but if my x is gone, then that with respect to x is really hard to deal with, and so we do something else. We say, okay, let's use a little bit of the chain rule idea and say if we can write dp dx as dp dy times dy dx. Oh, whoa, okay, so hang on. dy dx is p. then we can write the second derivative of y as p dp dy, because this should have a y in it. That's the idea. So if y is gone, it's easier, a little bit easier to see. You just do a straight up substitution. If x is gone, a little bit more involved, we have some p times dp dy, which gives us third case. What if both of them are gone? What if you don't have an x and you don't have a y? Choose this one most of the time because it's a little bit easier. So if you have a choice between them, if both x and y are gone, you just have derivatives of y up there, choose that one, a little bit nicer most of the time. So that's what I'm going to encourage you to do. So case 3 is what if they're both gone? So anyway, let's go ahead and give this a try. This is the idea. Hopefully it's making sense of what we're doing. Man, if you're missing a y, you don't have to replace the y with anything. Let's call the first derivative a variable, and the second derivative is just the derivative of that variable. It's going to reduce the order of our derivatives by 1. Something similar for x's, but we have to deal with the fact that x is gone, and so we're going to have a little bit of manipulation here to say, okay, the first derivative is p, great. The second derivative is p times dp dy, and we'll deal with that in the next video. Let's give this one a try. So, is it reducible? Is it a differential equation? Is it a second order differential equation that happens to be reducible? We start using some primes here because when we get to higher derivatives, it's very cumbersome to write the 2 everywhere and 3 everywhere and 7 everywhere if we get to that. So we deal with a lot of these primes, or when we get to higher derivatives and you write a third derivative, we'd write it like that. So that's a notational convention that we're going to use pretty much from here on out when we deal with these higher derivatives. So y double prime says the second derivative of y prime says the first derivative of y. Is it a second order differential equation? Is it reducible? Well, is it missing a variable? Yeah, it's missing the variable y. It has the variable x. So we're going to try to do a substitution. I don't want you just following rules. I want you to understand it. If we can do this and say, hey, let's just call p the first derivative of y with respect to x. All right. Well, then what's y double prime? What's the second derivative? Then the derivative of p with respect to x would equal the second derivative of y with respect to x, or y double prime. That gives us a very, very nice substitution that we can make. So are we still going to have an x? Of course. But this changes to x times the second derivative. Oh man, hey look, p was the first derivative. The derivative of p with respect to x is the second derivative. So y double prime is dp dx. Y prime itself, well, y prime stands for the first derivative. That's just p. That's it. Do you notice what it does? If you call the first derivative a variable, then the derivative of that variable is the second derivative. It's reduced the order of this differential equation by 1. Now, some notes for you. Do not forget to substitute back in. You're going to have a p floating around. You have to deal with that, and then you have to do another integral. So do not forget about that. And then secondly, because we have a second order differential equation, you should end with 2 arbitrary constants. We're doing integration twice on 2 different things, and so we're going to get that. So let's take a look at it. Now we have x dp dx. Okay, so our first order differential equation now is in terms of a dependent variable p with an independent variable x. It's separable. Let's separate this. So that means that we can group our p's dp and our x dx. We'll talk about domain a little bit. You're going to hear this quite often, but a lot of times you're going to hear assume x or y or these variables to be positive where convenient or necessary or something along those lines, and so they don't even write it. I think you should. We don't have to write greater than 0 here, but we certainly need to make sure that we understand that your first derivative can't be 0. That would, I mean, you'd have a constant there for your y if it was, so, but your first derivative can't be 0, but we're definitely going to want to say that x can't be 0. But you're going to hear that a lot, like assume these conditions to be positive where necessary or convenient. Well, okay, so let's see. First derivative is a variable. Second derivative is derivative of that variable. No problem. Separable, great. We got p's dp. We got 1 over x dx. Let's integrate both sides. On the left-hand side, we'll get ln absolute value of p. On the right-hand side, we'll get ln absolute value of x plus c sub 1. Well, that's kind of nice. Let's solve for p. Now, here's the point. You're going to have to solve for p, or have something that's going to be decent, because you're going to replace p with what p equals, which is the first derivative of y. So that p is going to become your first derivative. You're going to have to do another integral. And so we want to solve for p as much as possible so that our integration's easier. Well, what that means is that we're going to take these as exponents on e, so e to the and e to the. Well, that gives us absolute value of p equals, do you remember it? This would be e to the ln absolute value of x times e to the c sub 1. We know composition inverse functions, we're going to get just absolute value of x, but we can also do this. We can also say, let's wrap up those absolute values as plus and minus e to the c sub 1 times just x. All of this right here can be your arbitrary constant. Now, I'm going to leave it for just a bit. It's going to look kind of nasty, but I'm going to leave that there for just a bit to show you what's going to happen at the very, very end. So can you write this as c? Sure, you can. And you know what? I guess it doesn't really matter if we do or not. It doesn't super matter. If you want to write that as c right now, fine, but we're going to be changing it again later, so I'm going to leave it there. Now, the point of all this, the point is that, well, since this was a first order differential equation, it was fairly easy to solve. But now we understand that it was reducible. We're going to kind of have to unreduce it. We're going to have to say, well, p represents something. Don't forget to substitute back in. Your variable here is not p that you want to solve for, it's y. So if p represents the first derivative, that's the substitution we made. It yielded this substitution, so we're able to do both, like this double substitution idea we've been dealing with it for a long time. But now that it reduced the order, we solved it, now we understand p means dy dx. You go, oh, wow, that's still separable, actually. If we think about this as group your y's dy's and your x's dx, that's a really nice separable differential equation. Or you can think about it this way. You can think about it as that's basic integration. You could just integrate both sides right now with respect to x. That's fine. But we do, and we integrate, and we say, okay. Then on the left-hand side, we get y. On the right-hand side, we get plus or minus e to the c sub 1 x plus c sub 2. Oh, I'm sorry. X squared over 2 plus c sub 2. So integral of 1 dy is y, integral of this whole thing is a constant. So constant, we have x to the first power, add 1, divide by new constant. That's plus or minus e to the c sub 1 over 2, and then plus c sub 2. This is why we said we're going to get two arbitrary constants here. You integrate once, you get an arbitrary constant, it's still in there. You integrate again, you're going to get another arbitrary constant. It's still in there. So I mentioned something a little while ago that we're going to change this again. This is the reason why I didn't change it at first, is because I'm going to wrap this whole thing up in a constant. Could you have just said, let's make this c? Sure. And then this whole thing is c? Not a problem. And then this whole thing is c? Not a problem. This whole thing is c? Yeah, but you're going to have to wrap this up in a different c. So if you wanted to do this, I would suggest calling this c sub 2, c sub 2, c sub 2, c sub 2, and then c sub 3. That way we'd get y equals c sub 2 over 2 x squared plus c sub 3. Now I want to tell you one more thing. We're going to wrap this up as another arbitrary constant. And this is going to happen a lot in these reducible second order differential equations, that they represent families of curves with two arbitrary constants. So most of the time you'll see them A and B. So instead of C sub anything with these subscripts, you'll say, wow, let's just call this C sub 2 over 2. Let's call that an arbitrary constant A. And then C sub 3, let's call that an arbitrary constant B. And you're going to see that an awful lot. And what that means is that's a family of curves. Let's see, those are parabolas. Those are parabolas, upward opening or downward opening, narrow or wide, that have a vertex on the y-axis shifted up and down. Isn't that interesting? So this second order differential equation, the solution of that is a family of curves that are all parabolas. Very kind of neat. I hope you understand the technique. We're going to do 4 more examples that get a little bit more involved here. This is the most basic that I could get. But the idea is replace the first derivative with a variable that automatically reduces the order. Then the derivative of that variable represents the second derivative of your y. Replace them. Typically, we have a very nice integral. Just don't forget that this is second order. So when you figure out the first differential equation, you've got to solve for dy dx and do it again, or find some other technique to be able to do it again. Let's move on and check out another example. Let's learn about 2 more of these. So let's take a look at our second order differential equation, and we look at it and go, okay, I don't know how to deal with those. So unless they're super easy and we just integrate twice, no problem. But if they're reducible, then I can reduce the order of this differential equation by 1, do the integral, then do it again. And so what we're looking at is this idea that these are reducible if we have x missing or y missing. There's 2 different cases. In this case, we look at it and go, hey, y is missing. That's the nicest case because that's a direct substitution. If we replace the first derivative with a variable p, then the second derivative would be the derivative of that p with respect to x, the same variable. So first derivative, we call that a variable. Then the second derivative is just the derivative of that variable. Very nice substitution. Let's go ahead and do that now. So we're going to leave everything else, but we're going to replace the second derivative, y double prime, with the derivative of p because we can replace y prime, the first derivative, with p itself. So x, no problem. dp dx, no problem. Plus the derivative of y. The derivative of y with respect to x is p. Now we get 4x. What does it look like to you? Does it look homogeneous? Does it look like a first order? What technique fits it best? Well, it looks linear. And because we have this dp dx, we have p to the first power, we have a function of x, no, they're p's, they're not separable. Can I do it linear? Yes. Don't you have to divide by x? No. What do you mean, no? If you divided by x, you would get 1 over x here. You'd have e to the ln of, 1 over x. Said that all wrong. You'd have e to the ln x. E to the ln x would give you x. You'd multiply x back. You get exactly the same thing. This right here is actually the result of a product rule already. Look at that. The derivative of p with respect to x, leave the x alone. The derivative of x is 1, leave the p alone. That's the result of a product rule. So even if you want, you know what, I'll show it to you. If you wanted to go through and divide this, I'm going to erase this, but divide everything by x. Of course, x would have to be not 0, or you could put greater than 0, assume it's positive where convenient. We go, all right, well, e to the ln x, because integral of 1 over x dx gives you ln x. That would give you x. Let's multiply that. X gone x. Bam. It's the same exact thing. So even if you use an integrating factor, that integrating factor would be x. The thing that you're dividing by would be the integrating factor you're putting right back. It's like that first time I ever showed you linear. I said, if you've got to divide, right now you're dividing by that piece you're trying to find. Let's not do that. So this whole left side, that's the result of a product rule where you would have x and p. Notice, leave the first alone, derivative of the second. Derivative of the first, leave the second alone. That's it. That's the result of a product rule. Very cool. On the right-hand side, we just have 4x. It's ready for us. All we've got to do is take an integral on both sides with respect to x. We're going to do that now. Love it when it works out like that. Integrals, derivatives, awesome. We get x times p. Right-hand side, we would get, well, let's see, 4x, add 1 to the exponent, divide by the new exponent. That would be 2x squared plus c sub 1. That's our first arbitrary constant. Now, I've also mentioned, well, you probably should get p by itself if you can. So let's divide by x. Keep it in mind that x can't be 0 for us to do that. That's important. So what do we do? What do we do now? So after we have this, well, taken care of as far as our first order differential equation upon substitution, we need to understand that you cannot forget to resubstitute. This means something. This means the derivative of y with respect to x. So if p equals this, then this represents the solution to the first derivative. Now, thankfully, if we're able to solve for p, this is typically something very simple. So it's something to go, okay, yeah, derivative of y with respect to x, all I've got to do is integrate that. If I want to move my dx, think about this more like a differential form, cool. If not, take an integral right now with respect to x on both sides. Either way works. So let's write this as separating this separable equation in its most basic sense. Let's take an integral on both sides. This would be y equals, hey, that's x squared, plus c sub 1 is a constant, but we do get ln x. If we don't make the restriction that x has to be greater than 0, well, then we've got to show that this is absolute value. If you do make that restriction, you can omit the absolute value, plus c sub 2. Man, that looks pretty nice. The only other thing that we've got to do is, it's not super great to write c sub 1, c sub 2 all the time. It's not a problem. It just looks a little bit cleaner to write this as x squared plus a ln absolute value x plus b. That's the idea. If we're missing y, if we're missing the variable y, that second order differential equation is reducible. We call the first derivative a variable. The second derivative would be the derivative of that variable. Very nice. So use a technique to solve the first order differential equation that's the result of that substitution, and then replace that p, don't forget about that, with the first derivative and basically do it again. You should end with 2 arbitrary constants, either c sub 1, c sub 2, fine, or a's and b's, it does not matter. That's about it. The only other thing I would say is watch your domain restriction. So if you wanted to not have to deal with the absolute value, you'd have to define that differently. Just be careful with it. Okay, let's look at the second one. Why don't you try it right now? Take a minute and just write out what substitution would work. I'm going to erase this for just a second. But I want you thinking, is it a differential equation? Obviously. Is it a first order or second order? Well, obviously it's a second order. Is it missing a variable, which means it's reducible? Well, it's missing y. Oh, great. If it's missing y, then I can straight up do a substitution for the first derivative and then the result of the derivative of that, the second derivative. So let's call our first derivative p, and then the second derivative would be the derivative of p with respect to x. Do our substitution. So this would be our x squared, no problem. Second derivative is dp dx plus 3x. The first derivative is just p, and we have a 2. Isn't that nice? Man, that's so nice. I love it when it works out like that. Oh, man, what now? Well, now it's a first order differential equation. What's it look like to you? It doesn't look separable, not like the other ones. It looks linear. It looks like this one, as far as it's linear though, because we have a dp dx, we have add function of x times p to the first, no other p's, function of x over here, or at least a function over there that doesn't involve p's or y's or anything. Obviously not y's, they're gone. So let's try to write this as the linear that it represents. So let's divide everything by x squared. So this isn't as easy as the last one where we had that really obvious result of a product rule, which is nice. We're probably going to have to use our integrating factor here. Let's go ahead and do it. So one thing we'll want to note on our work somewhere, I hate breaking this up, but when you divide by x, you cannot have the x be 0, so we're going to write that. But since our integrating factor, if we don't want to deal with that absolute value, we're going to say, let's just make x greater than 0. And that takes care of the dividing by 0, we don't have that, and it also takes care of we don't need absolute values, so that's kind of, it's very nice. And you're going to see a lot of times, as I mentioned, that where convenient, write x positive or something, so it happens quite a bit. Okay, well now that we have our x's, or sorry, 3 over x being our p next to our p, well, don't worry about that. Think about the function of x that's going to be the exponent of our integrating factor. So when we do our rho of x, or integrating factor here, we have e to the integral of 3 over x, or 3 times the integral of 1 over x. That gives us e to the 3 ln x. That gives us e to the ln of x cubed. And so that gives us just x cubed. I hope that these are almost non-issues at this point, that you really understand integrating factor. We've done just a ton of them. Let's take that x cubed, let's multiply it everywhere. So we had a dp dx, we had a 3 over x, and a p, and a 2 over x squared. And we're going to take that integrating factor of rho of x in this case. Do you use integrating factors other places? Yeah, so I can't say this is the integrating factor, but it's an integrating factor that we're using here. So we're going to multiply by x cubed, and x cubed, and x cubed, all by distribution. On the left-hand side, this simplifies to 3x squared. Hey, look, derivative is this. Perfect. This simplifies to just 2x. So we have the result of a product rule where our product would be x cubed times p. On the right-hand side, we've just got 2x. That's really nice because we can just do a straight-up integral on the right-hand side. Looks really easy. On the left-hand side, same thing as long as we're with respect to x. So we're going to get this x cubed times p. On the right-hand side, we have x squared plus c sub 1. Let's solve for p as much as possible. Let's divide by x cubed. So if we divide by x cubed, we're going to get 1 over x. But we're also going to get c sub 1 over x cubed. So let's see, x squared over x cubed. Yes, 1 over x cubed. Okay, fantastic. Now, the reason why we solve for p is because if we can do that, obviously, I mean, hopefully it's obvious to you, that if you solve for p, then when you replace p with what it actually represents with this dy dx, it automatically makes something that's ready to integrate for us. It's already there. So we're going to do that. We're going to say dy is this 1 over x plus c sub 1 over x cubed dx. When we integrate both sides with respect to x, we get y. On the right-hand side, hey, that's kind of nice, I'll be in two fractions. This is ln x. We don't need absolute value. We made this domain restriction. And then we have, well, let's see. This would be c sub 1 x to the negative 3. So I'm going to add 1 to that. That's c sub 1 x to the negative 2 over negative 2 plus c sub 2. So we're trying to be careful here, watching our signs. So ln x minus, looks like c, you know what? I'm going to leave it that way. I'm going to leave it plus c sub 1 over negative 2 times 1 over x squared c sub 2. Why am I doing that? I'm doing that because I know I'm going to wrap this whole thing up as an arbitrary constant, probably a, and I don't want to have minuses if I don't have to. And then I have a c sub 2 hanging out the back. So we have this ln x, perfect. We have a leave your constant, add 1 that's negative 2 divided by the new coefficient. That's c1 over negative 2. That's going to be wrapped up as another constant, plus c2. So if we want to write this a little cleaner, we'd have ln absolute value of x plus, let's call that a. So if we have a times 1 over x squared, that's a over x squared plus b. And you can write that different orders, but that's about all we get out of it. I hope it's making sense, this idea. Hopefully you're getting it, what we're doing. Right now it should start being very straightforward in your head. Like, yeah, I totally get it, that the first derivative is a variable, second derivative would be represented by the derivative of that variable. Then undo the first order resultant differential equation, and then just integrate again. And you're going to get 2 arbitrary constants. I'm going to come back with 2 more examples. We got 3 to do. If there's one example you should really focus on, it's this one. This has a lot of really good stuff in it for you to know. Is it basic? It looks basic. It doesn't end up being all that basic. So y double prime, or second derivative of y with respect to x both times, equals x plus y prime, first derivative of y with respect to x, all quantities squared. You go, okay, hey, it's second order. Is it reducible? Well, let's look. Is it missing a variable? Yeah, it's missing the variable y. Can I make a basic substitution? Yes, I can. Let's go ahead. Let's call the first derivative p. That way, the second derivative is dp dx. No problem. Let's go ahead and let's replace that. So the second derivative, that's going to be dp dx. On the right-hand side, you don't replace your x's, but you do replace your first derivative. Remember, with every substitution, every instance of y has to be replaced. So both of our derivatives of y with respect to x have to be replaced. Thankfully, we don't have any y's. That's why we use this technique. So we don't have to replace that. So there are none of those to replace. That's why it's so streamlined. But then we have to the power 2. And you go, okay, what now? Let's just distribute the 2. X squared plus b. Don't freaking do that. But you can't do that. We have a derivative of p with respect to x, but we have p's and x's. Is it separable? No. Is it linear? No. What do I do? Hey, is there an obvious substitution that you can make? Yes. There's a composition right here. What if we called that composition V? Okay, what do I do with obvious substitutions? I solve for the dependent variable dp dx, because with an obvious substitution, you're trying to wrap up p, or well, all of this as a different variable, and then you're saying, but I need to leave my independent variable, get rid of my dependent variable. So I need to solve for p. I hope you remember this from these obvious substitutions. You call typically the composition, you call that some variable. You go, all right, well, let's solve for the dependent variable p. That way I can take a derivative of it and do a double substitution idea. The whole inside's going to become v, but then I need to be able to also substitute dp dx. Does that make sense? I've got to get rid of that too. All of the dependent variable must disappear, just like here it did. It's got to again. All right, well, so dp dx would equal, let's see, v is a function of x, so that would be 1 dv dx minus 1, because the derivative of x with respect to x is 1. So this chain rule, 1 dv dx, this 1. that gives us something we can substitute. So over on the right-hand side, kind of nice. You said this whole thing is v, so we have v squared. We said, all right, well, with obvious substitutions, solve for the dependent variable. That way, when you take a derivative of it, you can also replace dp dx, and that's exactly what we have. Whew. So wait a minute. So you're saying we can reduce the second order to first order, and then all of the techniques are open to us? Mm-hmm. So we did that, and we go, okay, how do you do that one? It looks like an obvious substitution. So v is x plus p. Awesome. Solve for your dependent. P equals x minus p. Do a derivative. Why? Because if you're going to replace that p, you better replace the dp. And so we've done that. dp dx is dv dx. That's a function with respect to x. Okay, minus 1. Awesome. And now, do our substitution. So that's v squared. Cool. This is dv dx minus 1. Awesome. What in the world is that? Well, it's not linear. Notice that dv dx, v squared. Not linear. Separable? Yeah. Let's add 1 and then have 1 over v squared plus 1 equals 1. Hey, that's a separable equation. Let's group our v's dv and our constants, or dx. And now we are ready to integrate on both sides. This looks pretty nice. Integral of v squared plus 1, I hope you remember it. Integral of v squared plus 1 is tan inverse v squared plus 1 equals x plus c sub 1. That's our first arbitrary constant. We're going to get 2 of them in this case. Oh my gosh, what in the world do we do now? Well, man, before we do substitutions, it's awful nice to... Wow, that was brain dead. Sorry guys, that should just be v, not v squared plus 1. I don't know why I did that. Tan inverse of v, just on a roll I guess, equals x plus c sub 1. Just like v squared plus 1, what? So anyway, the integral of 1 over v squared plus 1 is tan inverse of v, not v squared plus 1, equals x plus c sub 1. Great, okay, now what? Well, we've got to substitute back in for v, but I like to solve for v first if I can. Let's make v equal to tangent of the right-hand side. So if tan inverse of v equals x plus c sub 1, then v itself equals tangent of x plus c sub 1. All right, let's keep on moving. Now v equals something. What's v equal? So we use the substitution to get something we can work with that's separable. Let's replace it. So v is x plus p. Okay. This is looking a little bit better or worse, depending on your perspective. But wait a minute, p means something. Oh, I like to solve for p before I replace it. Are you noticing this? Solve for the variable that you're trying to resubstitute for before you substitute. It's way cleaner. So let's do that. So p is now tangent x plus c sub 1 minus x. Okay. Well, now what's p? Oh yeah, hey, p was pretty nice. P was just dy dx. That's separable in and of itself. And if we take an integral on both sides, we get y equals, if you take an integral correctly, where it's supposed to go, on both sides, we get y, oh my gosh, what in the world is tangent? Integration table should be let's see, ln, should be ln of absolute value of, what is it, secant? Oh yeah, so ln, absolute value secant, x plus c sub 1 and absolute value minus x squared over 2, or 1/2 x squared. Plus another arbitrary constant because we had 2 different integrals that we're doing. Not the same as doing an integral on both sides and getting two c's that you can combine. This is different. You're integrating an arbitrary constant from a previous integral. That's a different idea. So we have y, great. We have ln, absolute value, secant, x plus c sub 1, and then x squared over 2 plus c sub 2. Let's just call our arbitrary constant something slightly different. A's and b's are what you're mostly going to see. So y equals ln, absolute value, secant, great, x plus a minus x squared over 2 plus b. So, great example for you to see. Man, I hope it makes sense. That you understand, yeah, you have a reducible second order, but when you reduce it, you might have to use other techniques here. So you might have to dig deep and go, that's an obvious substitution. Call it v. Solve for your dependent variable. That way you take a derivative, you replace your dp dx, your d dependent variable over x. Great, work it all out. Solve for the thing you need to replace. Replace it. Solve for the thing you need to replace. Replace it, and then integrate again. And then we end up with something nasty, but that's the right answer. Okay, I think we have one more to do, and then we'll be good to go. So last example here. We're dealing with these second order differential equations that we can reduce to a first order differential equation. Solve that first order with techniques that are known. Replace it with the derivative that we substitute for, and then do an integral again, getting two arbitrary constants. Now, we run into this last one that's not nearly as involved as our previous example, but I want to show you what to pick, what option you should go with if possible. So we have second derivative of y with respect to x both times equals the first derivative of y squared. Is it a second order differential equation? Yes. Is it reducible? Yes. Why? Well, because it's missing y. But wait a minute, it's also missing x. That's true. And so you get to pick which option you want to go down. Most of the time, the missing y is easier to work with because the substitution is nicer. So when we look at this and go, hey, I'm missing x's and I'm missing y's, you do have options. You can go with either case. Now I haven't covered missing x, but I would suggest that you go with missing y because it's easier, especially for this case. So let's try it. Let's just replace our first derivative with a variable. That way, when I take this derivative of that variable, I can also replace my second derivative. And let's try it. So the second derivative of y becomes dp dx. The first derivative of y becomes p squared. That's about as nice as it gets. So keeping it simple is really nice. And using the missing y option rather than missing x option typically keeps things a lot cleaner. The other option works, but this is going to be cleaner for us. So let's continue with it. Hey, it's separable. Let's pull our p's over. Let's go ahead and integrate. So when we integrate, we have an integral of p to the negative second power, dp equals integral dx. And we get this add 1 divided by new exponent equals x plus c sub 1. We're going to clean it up just a bit. So let's see, negative 1 over p equals x plus c sub 1. You know, I don't like that negative, so let's solve for p as much as it's possible before we start replacing p with what it actually is. So negative 1 over p, let's multiply everything by negative 1. That would be negative x minus c sub 1. All right, 1 over p equals, you know what I might do right now? I might take this guy and call this c sub 2, because I don't want to deal with a negative. So c sub 2 minus x, that's fine. Hey, now we can reciprocate and get that p equals 1 over c sub 2 minus x. We've done all of this stuff before, we're just now wrapping it up in this new technique. Now that we've solved for p, we can replace p with what it actually equals. So p is the first derivative of y with respect to x. Let's show that. when we solve for that p, it makes the rest of this problem really, really nice because all we've got to do is integrate both sides with respect to x. So when we do that, when we integrate both sides with respect to x, we get y equals, let's see, it's u sub. U would be c sub 2 minus x. The derivative is negative 1. So this would be a negative ln absolute value c sub 2 minus x plus c sub 3. We're down to our next arbitrary constant. Yeah, that's about as good as I think we can make it. The only other thing we'd do after this is maybe switch some stuff around. Call this c sub 3 minus ln absolute value c sub 2 minus x. And then because sometimes we don't want to work with subscripts, we can call these two different arbitrary constants. We'd say a minus ln absolute value b minus x. That's about as good as it gets. Man, my goal is always to explain things to a level that you actually understand them, the reasons behind them, and are able to do them. So I'm hoping that's happened here. The idea is if you have a second order differential equation and you are missing a y variable, call the first derivative p, call the second derivative dp dx. So we're replacing the first derivative of the variable, therefore the second derivative is the derivative of that variable. Works out really nicely. Just don't forget the two main things. When you do your first solving of your differential equation, you end with p, solve for your p, you need to replace that with what p equals, and then you're going to have to integrate again. You get two arbitrary constants. I'm going to see you for the next video, and we're going to talk about how this all works if we're not missing y, but we're missing x. Here we were missing both of them, so it didn't really matter, but this way is going to be cleaner, and that's typically the case. If you're missing both variables, choose the missing the y one or y gone. I'll see you for the next video when we discuss how to do these second order differential equations that happen to be reducible by missing an x variable. Have a great day.